So in the last lecture, we talked about calculating the pH of a strong acid and strong base. So we're now going to talk about calculations that involve weak acids, and then next lecture we'll be talking about with weak bases. So what you want to do is you want to first think about why we have to do this, why are calculations involved. So whenever you look at any kind of a weak acid, so I'm going to use HNO2, which is a weak acid this time. So when HNO2 undergoes hydrolysis with water, it's going to form the H plus, really the hydronium ion, like we talked about earlier, an NO2 minus ion. Okay. Now for a weak acid, most of it remains at HNO2 and only a teeny tiny bit of H plus and NO2 minus ion. So we cannot assume that the concentration of the acid equals the concentration of the hydronium ion. In fact, that's far from the truth. So HNO2 does not equal the H plus concentration. So we no longer can take the negative log of the acid concentration to find out what the pH is. Okay, so let's look at this problem and see what exactly is happening. Okay, we're given a weak acid, butyric acid, and talking about how when it dissolves, when it's in solution, it gives you that pH. So what we have to do is we need to do an ice table, and I'm going to go ahead and use HA to represent butyric acid. And I want to show its hydrolysis equation fully to show it reacting with water. So that becomes A negative and H3O positive. Okay. Then the Ka is just a version of the equilibrium expression of the product over the reactant. A negative, H3O plus, all over HA, and of course we ignore water because it's a pure liquid. Okay, so ice table time. Gonna cross off the H2O. And the initial concentration of butyric acid is 0.0100, and you have none of these. Okay, now the pH is 3.39. So you should use your understanding of logarithm to know that the H3O plus concentration, also known as the H plus concentration, is 10 to the negative 3.39 power. And that would give you a H3O plus of approximately 4.1 times 10 to the negative 4th power. So that's the H3O plus concentration. And that increased by a factor of 4.1 times 10 to the negative 4. And because the 1-to-1 ratio, this is the same thing. And then also minus 4.1 times 10 to the negative 4. Okay. And we can go 0.01 minus 4.1 times 10 to the negative 4 to give you a value of 0.00959. Which you notice is actually not that much different than the initial concentration of the HA, which should make sense because it's a very weak acid. So the products are going to be heavily unfavored compared to the reactant. Okay, you have much, the 0.00959 is much greater. So the Ka would equal 4.1 times 10 to the negative 4 over 0.00959. And we can go ahead and put that in the calculator. Okay, and you can maybe square that and then say 0.00959. And that would give you approximately a Ka value of 1.75. So we'll say 1.8 times 10 to the negative 5. And again, that Ka value is much smaller than 1, which indicates that butyric acid must be a weak acid as stated in the problem. Okay, so that's like an intro to what exactly Ka is. It's basically the equilibrium constant that's associated with the equilibrium involved in the hydrolysis of a weak acid. Okay, so let's then talk about how we're going to use the Ka value this time to figure out what the pH is. Okay, so propionic acid, I'm going to go ahead and actually for this one, just for the sake of practicing, I'm going to write out the entire hydrolysis of this one using the complete formula. Hg3H5O2. And when it reacts with water, technical hydrolysis, it becomes C3H5O2 negative and H3O positive. Okay, the Ka expression would be C3H5O2 minus H3O plus over the reactant. Okay. Now, let's set up the table. Initial, change, equilibrium. The initial value is 0.10. X out this column, 0 and 0. And in order to find out what the pH is, we need to know what the H3O plus concentration is. And we don't know that, so I'm going to put an X right here to indicate that's what we're looking for. Therefore, this will go up by a factor of X, and this will go down by X. So X and 0.10 minus X. Okay. Now, for solving, we're going to put this in as 1.4 times 10 to the negative 5. That's the Ka value given to you in the problem. The C3H5O2 is X, and this is X, and then this is 0.10 minus X. And you can use the calculator to solve this by graphing the left side and the right side separately under y1 and y2 and seeing where they intersect, and that will give you a pretty close to the approximate value of what X is. However, because the value of Ka is very, very small, which indicates that reactants are heavily favored, we can make the assumption for now that the value of X is so small that it will have a negligible effect on the pH. So for now, just to simplify our calculation, we're going to say that the equilibrium value of the acid is 0.10. So that would enable us to simplify our calculation to say right here that 1.4 times 10 to the negative 5 equals X squared over 0.10. Okay. So when you solve that, you're going to multiply both sides, of course, by 0.1. And we're going to then square root both sides to give you X is approximately equal to 0.00118. Now, it's a good idea to do what you call the 5% condition, where you calculate the percent ionization. So you take the H3O plus 0.00118, divide that by the initial concentration of the acid, 10, and times it by 100. Okay, and then when you do that, you get roughly 1.18%. And that's less than 5%. So we can conclude that we can follow our assumption. Our assumption is okay, and we can go ahead and ignore that value of minus X on the 0.1. Okay, if it was greater than 5%, you're going to have to do the quadratic formula or graphing the left side and the right side and seeing where they intersect. But we can just say that x is approximately 0.00118. Okay, so then to calculate the pH, because that x is also the value of the H3O plus, we can say the pH equals the negative log of 0.0118. Okay, here we take the negative log of that, 0.0118, and say that's 2.93. And that would be, of course, your final answer. Okay? And so that's how you would calculate the pH of a weak acid by doing an equilibrium calculation. Okay, so up to this point, we've been dealing with the monoprotic acid, which is when you have one hydrogen at the front, and that hydrogen is the one that's ionized when it reacts with water. Okay, so a poly means many. A polyprotic acid is one where you have more than one hydrogen. So examples of polyprotic acids would be H3PO4, H2SO4, etc. So anything with more than one ionizable hydrogen. Okay, so if you look at the first one, this is the hydrolysis of H2SO3. It's going to break up to form H plus and HSO3 minus. And this indicates that this is a weak acid. Okay, then the HSO3 negative is the conjugate base of H2SO3, but then in the next line it becomes an acid, and when it gives up a hydrogen, it gives another Ka value that's even smaller, so this is even weaker. Okay, and you gotta think about why that's the case, is that it is going to be easier to remove the first hydrogen in this problem as opposed to the second hydrogen, because now the second hydrogen is now bounded very tightly due to the negative charge of this overall molecule. So it's going to be harder to remove that hydrogen so that it can be ionized. Okay, so that's why Ka values, successive Ka values get smaller and smaller as each hydrogen is removed from a polyprotic acid. Okay, you want to make sure you guys understand, though, that for later on, that this is the acid, and then this is the conjugate base. So the Ka goes with this acid. Okay, then when the HSO3 negative, if it undergoes further hydrolysis with water, it is now acting as an acid at this problem, and then SO3 2 minus is now a conjugate base. So the Ka for the first one is associated with this acid, and then the Ka for this one is associated with this acid, okay, which was the conjugate base in the previous one. Okay. Now, to determine what K is for the overall reaction, this is when you cancel out the HSO3 negative on both sides, and you end up adding the H pluses to give you two H pluses. When you add the two lines together, you would just multiply the first Ka, I call it Ka1, times Ka2 to give you the overall K. So we'll say 1.7 times 10 to the negative 2 times 6.4 times 10 to the negative 8 to give you the K for the overall reaction here. Okay, I'm going to go ahead and calculate that for you and tell you that that is 1.09 or 1.1 times 10 to the negative 9. Okay, and that's just a reminder about how to add to equilibrium. You don't add the K values, you multiply the K values together. So that ties back into the equilibrium basic lecture. Okay, so that's it for this lecture. I'll see you next time for the weak basis part.